So, gentlemen, I am Dmitrijs D.Bezrukovs. I'm a researcher of Ventspils International Radio Astronomy Center. And my charge in the center, one of charges, is the implementation, a practical implementation of microwave observation of the sun with a radio telescope. I'm hard radio astronomer, so I could tell a lot about solar radio astronomy. And in this presentation, I would like, at least, just to introduce some points, some problems, some ideas of solar observations which can be performed now, in the Ventspils International Radio Astronomy Center with the main instrument radio telescope RT-32. So what the first? As an introduction, I would like to tell you some words about why microwave observation of the sun. Why microwaves? Why microwave observation of the sun is significant for solar physics? Why it is interesting for us? As understood, nevertheless, that we have a lot of instruments on spacecrafts which is studying the sun. Still, microwave observation exists and very big instruments exist for it. The main idea of, I would like to show you this picture, maybe it is old picture, a known picture. It is a simulation of active region of the sun in corona. And a main idea of microwave observations and microwave, that the fact that the microwave emission, it is polarized. Microwave, it means the wavelengths, emission of wavelengths from 1 to about 10 centimeters. I'm not speaking about the long wave emission of the corona. It is some another physics, another company, another instrument. Microwave emission is produced in upper hemisphere and lower corona mainly. And maybe main point that it is how to say better, the place of creation of the microwave emission is very located. You can see on this picture the sunspots, photosphere, sunspots, magnetic lines, and the places of for 3 different wavelengths, the places of creation of emission is the some cups, one above another. So studying the analyzing the microwave, the polarized the polarization and how to say better, we can to localize the first localize very precisely localize the place of emission, and another point is that we can to obtain the parameters of plasma in these places. So, and I want to point that it is possibility of direct measurement. Of course, it is not simple. It is it have its own methods, but it is measurement. It is not simulation. It is speculation, imagination. It is a direct measurement of plasma parameters of atmosphere, solar atmosphere, and induction of magnetic fields. So I'll say it later. So, and what is interesting, how which problems of tasks and problems in solar physics which could be solved using based on the microwave analysis of microwave emission of the sun. It's mainly it is observation of a large scale coronal areas as active regions, coronal holes, a lot of problems. Another big problem is the coronal magnetography. It is clearly seen magnetograms on the photosphere of the sun, but what happens in the magnetic field in corona is, it is interesting, but it is not so accessible. And another, it is new, actually it is a new challenge for us, for our radio telescope. It's the analysis of microwave fluctuation, of microwave flux of local sources, which could be analyzed. The analysis could be used as precursors of solar flares and show us a flare could give us possibility to analyze flare activity. So, what instruments we are having now for it? The observation, microwave observation of the sun, now the situation is not so brilliant. If I'll try to make this chart of day, time and wavelength chart of possible observations, I'm speaking about sun-dedicated instruments, so-called sun-dedicated instruments. So the instrument which is observing the sun only and observing permanently, observing regularly routine observation and the accessible data archives. Actually, now we have two big instruments in the Eastern Hemisphere. Is this abbreviation MUSER? Its instrument is located in Inner Mongolia in China, and abbreviation the place is I'm pronouncing correctly Mingan-2, and abbreviation Mingan-2 solar radio telescope. And another instrument in the Western Hemisphere is the American instrument EOFSA, Extended Owen Valley Solar Array, as I remember. And another instrument, of course, solar observation and radio astronomy is made. A lot of it is made, but it is made so occasionally, and now most of instruments, standard-dedicated instruments, as Nebiyama, radiograph is closed now. Some radio telescope is not accessible, and so on and so on. And if we could organize,
the sound disappeared.
If you could organize routine observations of the sun, regular observation of the sun with our radio telescope, you can see its amount of information we could obtain. Our center could have maybe small, but it's honest place. It's another instrument, Mitsahove radio telescope. It's one single vision, one channel, but this guy is working permanently with the sun by his own. So maybe I did not say the main thing that the Ventspils International Radio Astronomy Center has the ability to observe sun permanently, make a routine observation. I will continue with it. So, and here you can see how looks radio telescope R32, 32-meter dish. and how it is looks after construction of the central cabin. You can see the central cabin was extended to install a lot of instruments now. And more interesting, it is changed the secondary mirror to organize active, how can I say, moving the active actuators position of secondary mirror to organize the active antenna mirror. The main instrument for solar observation is now used this gray box. We call it low noise spectral polarimeter, LNSP for this abbreviation, for because it is a fourth version. Now it is installed, and you can see how it is installed on the roof of the central cabin, and how looks this one is the feed, wideband feed for our solar observations. I will not I will not say about. I will not say about the first. This receiver is integrated in the system or data acquisition. We say data acquisition system and antenna control system, and to provide at least to almost automatically to provide the routine observation of the sun. I will not say about the kitchen of scanning, data storage, data processing, cleaning, and so on and so on. As a result, so here you can see some data of the receiver we used. Mainly, I did not say again. Main feature, it covers the wavelength range from 2.1 till 7.6 centimeters, and this range is divided to 12 frequency channels, and it is maybe not very interesting, but this distribution of frequency on frequencies channel by channel corresponds to this known grid of frequencies made by Kaidanovsky, Gelbrich in early 60s, and corresponds to frequencies of Ratan 600 solar, they call it solar polarimeter, not solar polarimeter, solar receiver, let's say. So here you can see the result of one routine observation. It is a simultaneous set of 12 channels, so 12 set of 12 maps, two-dimensional maps of two parameters, Stokes E parameter. You can see looks for it for wavelengths, shorter and shorter. It is 7 centimeters, as I remember. 7 centimeters, it's about 3 centimeters. You can see how it changes. You can see at least 3 active regions this day. It's in November. Oh, yes, it's in November. It's in November or October. It's October. It's October of the 2024. Active regions. How changes brightness temperatures of relative brightness temperatures of active regions. It's shorter. And another, the same picture, it is a Stokes V parameter, show us the polarization of active regions. You can see quite some is not polarized, and active region are polarized. And maybe most interesting here, and you can see here how changes polarization of active region, which is approaching the limb and depending on the wavelengths. Classic study book. So, and you can say we can obtain almost automatically, we can obtain this routine observation. It is stored in some archive. We have maybe small, but it's accessible archive of observation. And this observation could be used for different of solution of different solar physics problem. I'll try to show you some problems we touched with, and we try to solve it. The first one problem, maybe it is maybe simple, maybe very trivial, but the problem is to calibrate the brightness temperatures of microwave emission of the sun. It is a problem. Actually, it is a problem. It is there is some works about brightness temperatures of the quiet sun, but it is a problem. It is and if we have the two-dimensional maps of the sun, it is possible. So another problem is the visibility of coronal holes in microwaves, because coronal holes is clearly seen in the ultraviolet in optic nerve. In ultraviolet, you can see in the ultraviolet as the source as the vacuum. Probably it says the solar dynamic observatory. In ultraviolet, you can see two coronal holes, and these places here is a quite, you can use it in quite some active regions, and you can see the clear spectra of active region. It is rising with the bandwidth, and coronal hole have decreasing the spectra very classically as the book. So I want to say that it is for our observation, it is possible to clearly detect and clearly observe the coronal hole itself. Another so here you can see how looks extended coronal hole, and how it extended coronal hole is visible on our observation. Another problem, interesting problem, we are at least interested in. And the interest to this problem is rising now. It's a problem of so-called extended coronal structures, which is associated with the open magnetic field, and which would be expected as a source of slower wind. The main idea is that if we have maybe the sun, not we, sun have the system, this it's an equatorial area, the system open of magnetic line, which produces the similar this one, extended coronal hole-like area, which could be expected as a source of solar wind. You can imagine if you have the open magnetic field, plasma is coming along the magnetic field and blowing out from the equatorial area of the sun. And to understanding actually now there is no clear terminology. We use the term narrow coronal corridor, this one. There is another term, coronal pattern, the dark coronal corridor, SWAP, and so on and so on. The interest for these areas is rising, and we are trying to solve such a way. You can see these dark areas. This one for one wavelength and for another wavelength. And this green points is a so-called squashing cofactor. It actually shows us this vertical open magnetic field line, which is simulated from the magnetogram from the photosphere. It's almost correlated. And if we will take the cross-section of this, no, let's say it is the coronal corridor. If we take the cross-section of this coronal corridor and analyzing the observation and Nabiyama heliograph observation, it is, you can see, it's an attempt to simulate the structure of this cross-section of coronal corridor. You can localize that the place where the microwave emission creates for different wavelengths. We can obtain about electron densities of plasma, rather reasonable. Physics is reasonable, and to obtain also induction of magnetic field. Seems it is reasonable. So it's of course it is a big work. It's just some words about the work where we do. We did and we are doing now, but it is a rather wide field. So another, it's, I thought it's our challenge for us. It is observation of solar flares and let's say correctly, observation of microwave emission bursts, which is correlated with the solar flares. Those solar flares itself is a rather complex event, and it has many manifestations. And one of these manifestations is a burst of microwave emission, which is emitted from the legs of coronal loop when this reconnection happens. Reconnection of magnetic line happens, and all this process happens. For us, it is interesting because then fluctuation, so-called quasi-periodic pulsation or fluctuation of microwave emission could be expected as precursors of solar flares. That should be interesting. And what we may feel, here you can see some example of this kind of observation. We observed our main point that we could observe the separate active region, not whole, and the burst not fluctuation, not fluctuation of the microwave emission, not from the whole disc of the sun, but separate active region. it should be interesting. And here you can see the example. It's here is ultraviolet in ultraviolet. No, it's a X-ray from X-ray from satellites GOES 16 satellite to flares, to clear flares, and we can see it has disappeared. That was calibration moment. We can see the burst, microwave burst for 5 frequencies, how it looks, which is correlated with this flare. So, and if we will expand in time, you can see the profile of for intensity, the profile of intensity of this burst. And more interesting is the profiles of polarization of this burst. What does it mean? I don't know. It is necessary to understand why this changes of polarization happens. So, so this is another problem we are trying to solve with our observations. So, and the last maybe exotic is not maybe very scientifically valiant, but it is exotic at intelligent. It's observation of the sun eclipse, which were made in the 29th of March. Here you can see the profile of for 3 frequencies and moments. The first optical contact, the maximal phase of observation, and the fourth optical moment that is here. The main idea of the eclipse observation of the sun, radio observations of the sun, is that the moon is working with its sharp edge, is working as interferometer, and analyzing the profiles of the flux, it is possible to reveal the fine structure of active region. In this case, it is this active region, the moon, for us, the moon did not cover the active region, it is here, it is active region. In this observation, so this, I didn't say, this yellow point is half power beamwidth of antenna at 7 centimeters. We observed the point on the limb, and you can see the common drop of flux, and this common drop is overlapped with some fluctuation flux, which is connected with a fine structure of the corona over the limb. It is mainly. And during the it is caused by moon age, and sun is rotating during the observation. The sun rotated itself. So no, it is funny, but it is maybe it is not very interesting. So maybe I will stop. So the summary conclusion of my presentation, it may be the main idea that the microwave observation of the sun is performed by Ventspils International Astronomy Center and remains a significant part of its scientific activity, and we are trying to do our best. So, thank you. I didn't say. The work supported by 2 projects of LZP, Latvian Council, Scientific Council, these numbers, and abbreviation STEF and FLAIR. Thank
Okay,
you for listening.